In this video, we'll be discussing how distance vector routing algorithms work. Let's get started. Today we continue to consider routing algorithms as part of the network layer control plane. In the last video, we looked at the link state routing algorithm, and today we'll be looking at distance vector. The distance vector algorithm is based on the Bellman-Ford equation. As a reminder, routing algorithms are the formalism that defines how paths are discovered through the network. Later on, we'll look at routing protocols, which include all the implementation details needed to make a routing algorithm work in practice. The Bellman-Ford equation is an example of dynamic programming. It basically says that the least cost path between nodes x and y is the minimum value of any sum between x and one of its neighbors, and that neighbor and the destination y. So we have the direct cost between x and v, its neighbor, and the cost between v and y, the destination. We then iterate over all the neighbors and find out which of them has the least cost path. So we'll go back to the same example that we used for looking at link state, with our source u and destination z. Each of u's neighbors know their cost to get to the destination at this point because the distance vector algorithm has been running for some time already. So the cost from v to z is 5, using the path xyz, and the cost from x to z is 3, and the cost from w to z is 3. So then applying the Bellman-Ford equation, u will look at its direct cost to the three neighbors and the neighbor's cost to get to z. Plugging in the numbers, we see that our smallest cost is 4. This is using u's neighbor x. So u's distance vector will record a cost of 4 to get to z. Once it's completed this process, each node will send out its new distance vector. So then each node will have the updates from its neighbors and use the Bellman-Ford equation to update its own distance vector, and then repeat the process. Over time, all the nodes will converge to knowing the actual least cost to each of the destinations in the network. So each node waits for a change, either in the cost of a link that's adjacent to it or an update message from a neighbor. It then recomputes its distance vector, incorporating the change, and sends out its new distance vector to the neighbors if anything has changed, and then repeats the process. So we can see that this is an iterative and asynchronous process. It's also completely distributed, and it will naturally stop when there's no more changes to be made. So let's look at this in the context of another network example. Time 0 is our initialization, where each node only knows the cost to its direct neighbors. So in A's distance vector, we see that the cost to most of the destinations is infinity, and it just knows the direct cost to B and D. We also note that we've got one extra high cost in this to keep things interesting, and one missing link between two of the nodes. So at the end of the initialization, all of the nodes will send out their distance vectors to their neighbors. We then begin the T1 iteration by each of the nodes receiving those distance vectors from their neighbors. All the nodes then compute their new distance vector, and they all send out their updated distance vector to their neighbors. We then begin the T2 iteration by receiving distance vectors from the neighbors, recomputing, and sending out the updated distance vector. And this process will continue until there are no more updates to be made. Now we'll go back to T1 and look at the computations being made at one of the nodes. So B has this distance vector after its initialization, where it knows its direct cost to its neighbors, and that's it. It's then going to receive distance vectors from its neighbors, including node A, node B, and node E. So B is going to apply the Bellman-Ford algorithm on all of these updates that it's receiving from its three neighbors. So going one destination at a time, B hasn't received any updates for destination A, so it still has just its direct link cost to node A. We then have destination C, which is in the same state. B has its direct link cost, no other updates apply to it. Then destination D, where B had a cost of infinity before, but now has two neighbors with updated cost to D, so it will take the minimum of those, making its cost to D 2. The cost to E is still its direct cost, but it has a new cost to F of 2, infinite cost to get to G, cost of 2 to reach H, and an infinite cost to get to I. So now B has an updated distance vector, which it uses to replace its existing distance vector. Over at node C, the same process is going on in parallel with node B. C has received B's initial distance vector, and is going to use the Bellman-Ford algorithm to recompute its own distance vector. C knows how to reach A, which it didn't before. The cost to B is unchanged. The cost to a number of destinations is still infinite, but it knows how to reach E with a cost of 2. This produces a new distance vector for C, and it also updates its distance vector. And we could continue on through the rest of the nodes in the network, computing their second round of distance vectors. E likewise receives distance vectors from all of its neighbors. It will go through those costs and add 1 to each because E's cost to each of its neighbors is 1, and so on. From a high level, we can see that this iterative communication process gradually diffuses routing information through the network. And we can quantify this. At initialization time, each node knows only its own information. But at the second iteration, C's information has propagated 1 hop through the network. At the second iteration, it's propagated 2 hops. At the third iteration, it's propagated 3 hops. And by the fourth iteration, it's propagated through the whole network. Because the longest shortest path in this network is 4 hops, we can say that the network's diameter is 4 hops. So we can see that the time taken for the distance vector information to propagate through the whole network increases linearly with the network's diameter. Here's another distance vector example. This one using a much smaller network, so we can look at all of the distance vector information known by all of the nodes in parallel. In the first column, each of the nodes just knows its own direct cost to get to each of the neighbors. In the second column, the distance vectors have been exchanged, and so looking at x's distance vector, we can see that it's going to update its costs to y and z. So it learns that z can get to y with a cost of 1. However, x has a cost of 7 to get to z, so this new cost of 8 is higher than the cost it already had to get to y, so the cost from x to y remains 2. It will then go on to recompute its cost to z, which was previously 7. It now learns from y that y can get to z with a cost of 1, and it knows that x can get to y with a cost of 2. So we have a new lower cost to get to z with a cost of 3. As we continue this process, we see that y has no updates. It already had the lowest cost to get to its neighbors. However, z learns that it can get to x with a cost of 3 via y. And by the second iteration, there's no more changes. The network has converged and the distance vector information has propagated and stabilized. We can also use this small example to look at what happens when the cost of a link changes. With respect to distance vector algorithms, we say that good news travels fast, and conversely that bad news travels slow. So let's see why that is. When the cost of a link changes, in this case to a lower cost or good news, the neighboring nodes will detect that. So in this case, we have the node y detecting the link cost change from 4 to 1. Y will update its distance vector and send that out to z and x. So z gets the new distance vector with the lower cost. It updates its distance vector and sends out that updated distance vector. Y gets z's update back, but because it wasn't getting to x through z, that doesn't affect y's distance vector, and so the process is completed. Likewise, x will have updated its own distance vector and sent that out, but it won't affect either z or y's distance vector. So after T2, the process is done. Now let's look at the reverse scenario where the cost increases. To illustrate this point, we're making a dramatic link cost increase from 4 to 60. So in this case, we have to keep in mind that z had already learned a cost to get to destination x of 5, and it was doing this via y. However, the distance vectors don't include the paths, only the costs. So z is advertising a cost to get to x of 5. When y observes this dramatic cost increase on its direct link to x, it will switch over to using the cost that it learned from z. So y will now say that it can get to x with a cost of 6 by going through z. Y will then advertise this new distance vector, and z will see that its cost to get to x has increased from 5 to 7, and advertise a new cost to get to x of 7. Y will see this, increase its distance vector cost to 8, send that back out, and this process just keeps ping-ponging back and forth between y and z until the cost exceeds 50. At that point, z will use its direct link to x instead of the path through y, and the process will stabilize. But we can see that this takes many more iterations than the example where the link cost was reduced, and hence the saying that bad news travels slow. Now let's do a little comparison between distance vector and link state. In terms of message complexity, we saw that in link state, order n squared messages must be sent because every router has to flood its link state information to every other router in the network. In distance vector, routers only need to communicate their distance vector to their direct neighbors, not to every router in the network. But because it's an iterative process to disseminate the information through the network, the convergence time will be longer and varying. On the speed of convergence issue, link state is quite fast because all of the message distribution happens at the beginning, and then all of the routers are able to compute their shortest cost paths to all the destinations simultaneously. In practice, convergence of link state algorithms happens in a matter of milliseconds. In distance vector, the convergence times vary, and while it's happening, there may be routing loops, such as we saw in the bad news travels fast example. We can also look at the robustness of the algorithms. Because each router in link state is relatively independent of other routers, meaning it computes all its own paths, it is relatively robust against any miscomputation by one of the routers. In distance vector, on the other hand, because of its iterative nature, each router is dependent on the computations of its neighbors and their neighbors and so on, so any error by one of the routers will propagate through the network, and in some cases, such as a router misbehaving and advertising very low costs to all destinations, it would be able to do significant damage by blackholing traffic. That completes our introduction to routing algorithms. In the next videos, we'll be looking at protocol implementations of these routing algorithms, starting with OSPF, a link state routing protocol. See you then. We hope you enjoyed this video. If you found it to be useful, please click the like button. To be notified when more videos are posted for this class, please subscribe to our channel and click the bell.